Hello everyone, this is the video lecture for Calculus 3, section 14.4, tangent planes. So, tangent planes are interesting because we're going from the 2D into 3D. Think of the 2D for a second. I have a nice little cubic here. Let's do a little tangent line. Okay, cool. So that's 2D. In 3D, well, I'm going to mess this thing up. In 3D, let's say I have like a I don't know, paraboloid or something like that. If I wanted a tangent plane for that at this point right here, so then I'd have this tangent plane coming off of it. That's still pretty bad. Let me do this. There. Kind of like a piece of paper that's touching only at one point, and therefore you can see that it's, well, it's your tangent line, kind of. It's just a tangent plane now. So what I'm trying to get at is the concept here is basically identical. How did you find a tangent line? How did you find this tangent line? Well, a line is mx plus b, isn't it? There's your slope. There's your derivative. Well, expand this one out a little bit. Do you remember having y minus 1, y1, m, x minus x1? This is almost cheating a little bit. Notice this format here. You see this right here? You see this? Let me see that the same way and move it over. So I got m, x minus x1, minus the factor of y minus y1 now equals 0. Isn't that strange? It's a different way to write it. We don't do that writing at all in algebra. That would be really silly. But you can see that we have our slope. Again, that's our derivative. Okay? And notice right here, this is a funny little guy. This is basically my dependent variable. I guess it's the highest order one. It's you got your xy plane, and then you're going up with z is going to be the same style, but it starts with a minus in the front. That is a characteristic required to make this formula work, okay? Let me now show you how this works. Here we go. So for 3D, what kind of formula? It's very, very similar to this. Here we go. Here's your tangent plane formula, okay? Tangent plane. I've got a x minus x naught. Instead of x1, we use x naught. It makes it easier, in my opinion. Plus b, y minus y naught, plus c, z minus z naught, equals 0. Now, this is a general plane equation. It doesn't have to be necessarily a tangent plane. That's just a plane equation right there. Some things to know. My v vector, or again, you can say like a vector ABC, is your slopes. Now, the fact that I'm making that a vector is kind of interesting. We will see that later. I can't remember if it's this chapter or the next one, but we will see how slopes interact with vectors eventually. We're also given our initial point, x naught, y naught, z naught. And so how do I make this slope thing work for me? Where's the math involved? Well, basically, it's z sub x, z sub y, -1. And then you have to do it at p. That's, again, how do you say that? That's at p. Or when p. Okay. This is my slopes. A, B, -1. Essentially, you'll always have a -1 there. And so that's a formula, I guess you can call it. Okay, let's try this thing out. So 14.4.010, they say z is equal to ln of x minus 6y. And they give me a point at 710 and say, what's the tangent plane equation? Couldn't be easier. So first off, let's find our slopes. Derivative in terms of x. Again, derivative of ln is 1 over stuff. Derivative of that stuff is going to be a 1 in this particular case. But we shouldn't stop there because it needs to be at the point P. Your slope is a numeric. It's a number. So we're looking for a number. What's the number going to be? Well, we plug in here. That's x, y, and z. So plugging in the x, y in particular into this, we get 7 and 1. 7 minus 6 times 1. So you get 1 over 1 is a 1. So that's your slope. That's your A in your formula coming up. Z sub y, same derivative as last time, but my chain rule says that I'm going to be getting a negative 6 multiplied by it. So that can go in the numerator. But again, I want to have it at P. So I'm plugging in that 0.71. Just like I had last time, I'm going to have the same... Oh, that's just a positive 1 there. And then times negative 6. You can guess my answer is going to be negative 6. This is my B. And whenever you're doing this formula, you'll always have your C is a negative 1. Always. Okay. I'm sure there's another formula for it, but this is a formula you'll use again and again as we continue going. I'm not going to go and teach all this new stuff on this section. We'll get there eventually. But this concept is very good. Okay. So then, my formula again, let me go and rewrite it. It's my generalized plane equation. This will always work regardless. So I got a 1, x minus 7. I got a negative 6, y minus 1. And then I got a negative 1, z minus 0 equals 0. Again, you can see my 0.710 right there. And then you can see my slopes, 1, negative 6, and then that negative 1 is always there. Simplify. So like distribute this guy, distribute that guy. X minus 7, minus 6y. 2 negatives make a positive 6. Minus z equals 0. Often they're going to want it not equal to 0, but they're going to want that z equals. So go ahead and move that over. That's an always. Just go ahead and move it over always. And so then we have z is equal to x minus 6y. Combine like terms to make a minus 1. And there is your plane equation. Okay, next question is a doozy. But it's a good concept, so I really like it. F of x, y, z is a fourth dimension thing. You put 3 dimensions in, you get a fourth one out of it. So I can't really draw that. It's not 3D. This is a 4D graph. But it would look kind of like an ellipsoid-ish. Hyperellipsoid. There you go. I have no clue. I was just making something up. So my point here is at 8, 8, 4. And they're wanting not a tangent plane necessarily. They're saying to linearly approximate. Linearly approximate. And then they give me this really weird value. 8.03 squared, 7.98 squared, and then 3.99 squared. Okay, isn't that weird? So we're jumping again from 3D, what we just had, now into 4D. Keep that in mind. What we had originally, way back up here, this was 2D, and we're going down to 3D. What's the difference? Well, M, this chunk here, is now going to be A and B. And again, that minus is always on the very end of it. So you'll always have a minus there. Just like we had right here, we'll always have a minus on the last one, on the dependent variable. So if you wanted to call this W or something else, that's fine. But this guy, whenever we start using it, or F, you can even just use F, is going to have that minus sign in the end. That's something to keep in mind when we keep going. If you were to put this in the calculator, I doubt it's going to allow you to get that answer because they want you to go through this process here. So what they're wanting to do is use a tangent plane, finger quotes here, it's not really a plane anymore, but think of it like a tangent plane, and we're going along the tangent plane to find an answer instead of the actual graph itself. So if that makes no sense, let me try and do it in 2D. Much easier, we know this stuff really well. Let's say I want to approximate that point there. Let's approximate that point given that I started with this point right here. So this is my starting point, and I find my tangent line from it like this. There's my tangent line. It just so happens to be at a maximum. It doesn't really matter. But notice that if I went to this x value here, I'm going to get a little bit different height than this guy right here. You see how my y values are going to be a little different? Let me try a different place, because that one's a little weird. Let's say I try to approximate this one, given that I had this tangent line right here. Now, I am not touching that point. Otherwise, it wouldn't be a tangent line. That's like a duh. But there is this small little y difference in between there. You can see there's my y distance to this point is not the same as the y distance to where it would be vertically on the tangent line. So there's this little delta y in there. And that's our error. That's our error. Okay. We're not looking for the error necessarily, but I'm saying we're using this tangent line, tangent plane type, tangent hyperplane or whatever, in order to get a different number that's not exactly this. And you might be wondering, well, why the heck am I doing this if I could just plug it in the calculator? Well, what if you didn't have a calculator? Dun, 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 dun. You can't do it. So good luck with that. So instead, we're going to try to do it, finger quote, neatly without a calculator, and we'll get something pretty close. Moving on. So from this function, I now need to find my slopes. So I'm gonna find my first derivative of this right here. Again, this is a big square root. Square root comes down. Leave the inside alone. So the 1/2 power comes down. Leave the inside alone. Negative 1/2. Take the derivative of the inside. It would be a 2x. For x, of course. Everything else goes to 0. So your half and your 2 are going to cancel. The x goes to the top. You leave a square root in the bottom. And you can see how my format is going to be for every single derivative. So that's for my x. Can you imagine what your f sub y is going to be? See what I mean? Could you imagine what your f sub z is going to be? Okay. But if you remember from the last problem, it's not good enough to just simply get my derivatives. I need them at p, at p, at p. And so I want to find out what is the actual slope, the numeric, the number that'll make that work. Well, our point was 884 right here, 884. And so I got an 8 in the top. When you put 884, you get 144. Square root of that's going to be a 12. And so therefore you're getting 2/3 out of this guy. This is going to be the same thing. When you plug in the 4 here, you get half of that. It's going to be a 1/3. So easy stuff. There's your numeric numbers. This is, I guess, an A, B, and a C. But my D, because again, I'm going into 4 dimensions here. This is my A, this is my B, this is my C. So now your D, what's your D? Can you guess? It's a -1. You got to have a -1 at the end. That's for your dependent variable. Here's the big formula. Here we go. I'll write the formula out just so there's no confusion. But I'm assuming at this point you're understanding what I'm doing here. See? And then we got a D. I'm going to use F and F naught. Okay. Notice that I just added on another guy. Keep on going. You just add on another term. If you got to go to 5D, keep on going. Just use another one. Just as if you went to 2D, you would only have 2. That's okay, right? If in 2D, you wouldn't even have any of that. You're done there. B is a -1. That's your slope M. Walk away. You can tell that there's a system here that we're using. Thankfully, we got all of our numbers already. 2/3 x minus the 8. 2/3. If only I can make that look a little bit better. Y minus 8. My C was 1/3. Just can't get 3s today. Z minus 4. And then D is always a -1. F minus F naught. Now that's an interesting thing. What's F naught and all that stuff? You know what I mean? We'll get to that. Don't worry about F naught for a minute. We have to get all this other stuff first. Go ahead and distribute so you can get a lot of numbers here. Actually, you know what? No, don't distribute. Don't distribute. Let's hang on tight for a second. I need to find out what this F naught is, I guess. Let's just go ahead and do it. And then I'll show you how to find out how to get your final answers, and we're done, okay? We're very close to the end. What's F naught? Well, F naught is plugging in my original point P into the function. And what was that? It was 884. So we would have the square root of 8 squared, 8 squared, and 4 squared. Which is funny because we already did this back up above. It was the square root of 144, which turns into a 12. So this guy right here is actually just a 12. Okay. F by himself, though, whenever you distribute this guy, F needs to move over. That would be a negative F right here. You move it over to make a positive F. So I'm going to do approximately... Though it is basically equal sign. It's, again, they're basically the same thing. But for technical sake, I'm saying it's approximate because we're doing a linear approximation. And then two negatives make a positive 12. Okay, so that's my formula. Well, remember the point that we were trying to find? Go way back up for a second. Right here, this guy. This is an X, a Y, and a Z. Obviously, you can see what's going on there, right? So my X, Y, and Z, I'm going to plug in just as you see them. Literally to that point, I guess you can call it not point P, but point Q now. Your second point is now at 8.03, 7.98, and 3.99. So plugging in this Q, I should get my answer. Notice that I'm basically trying to find out from my P, I'm now trying to find out the value for Q. That's what's really going on here. I found my derivative. I found my slopes at P. Everything was focused around this guy. And then I went back and said, okay, well, now approximate Q. Okay? So plugging in my new numbers, I got here we go, 8.03 minus the 8, 2/3. This was 7.98 minus the 8. And then my Z, 3.99 minus the 4 plus 12. Calculator for sure, 12.0033333. I'm sure you can probably get a fraction out of it, but they wanted a decimal. There's your answer. We're done. Whew. Man, that was just question number 2. There's actually not a lot of questions in this section, but they are a little different. There you go. Now, this is not what the book did at all. The book does something wildly different. That's okay for the book. I think this way makes sense. That's why I did it with you. Okay, next problem. I got 14.4.033. I got Z is equal to e to the negative 5x cosine of 2 pi t. And they're wanting... This is kind of funny format. dz is equal to blank dx plus blank dt. And really what they're wanting to say here is this is z sub x and this is z sub t. And that's all it is. It's just partial derivatives. I'm not going to get into all the hairiness of how this and divide and comes back to... Nah, it's fine. So take your derivative here in terms of x. Well, there's no x's over here, so you're focused on that guy. The negative 5 comes down. Leave the other stuff alone. So that's your answer for part A, essentially. Derivative in terms of t, nothing there, but right here, so you leave the first part alone. Derivative of the cosine is going to go to a negative sign. Go ahead and put a minus sign in the front. Sine 2 pi t. Derivative of that on the inside is going to make that 2 pi come to the outside as a multiplier. So just to make it look nice, not really required, but it makes it look nicer. There you go. Okay. So that's your part B. Next problem. Oh, sorry about that. I actually only have 2 more problems, so that's good. Okay. Whoa. Let's start a little bit over here. 14.4.039. So I've got now z is equal to 7x squared plus y squared. They're saying that they're wanting to go from 1 comma 1 to 0.95.9. I thought that was kind of weird. And they're saying, well, find dz and then find delta z. All right. This here is a Calculus 1 problem. I'm not going to go way deep into it. I'm going to try to remind you of a couple things. But these numbers are similar but different. How I remember them is that this is calculus. Oops, if I could spell calculus. While this is, I don't want to say geometric, it's just more like physical. It's like physical. It's like measuring. There you go. It's like measurements. Like you get a tape ruler out kind of thing. So the D means derivative. Delta means distance. Means a distance. And so that's how I kind of remember the differences here. Well, calculus is like super easy. So here, how do you find it? What's your answer for this? Well, dz, here's your formula, I guess, is del z, del x, delta x, plus dz, dy, delta y. Notice that delta z is not the same as these guys, but it's kind of similar in understanding. This is a distance, a difference from the original. To zoom out, here's the zooming out. This is kind of funny, isn't it? Zx, x minus x naught, and zy, y minus y naught. You just saw that a second ago, didn't you? Look at this. There's no change, and then you can have other stuff, but that's the same thing as the tangent plane equation. Again, how did they get this dz there? Well, they had a negative. I guess this would have to be 0. This is a whole new problem now. And so then you would have your z minus z naught, and then you take a derivative. I don't know. I'm just saying, you don't really need any of that. I'm just saying the idea is the same as what we just saw a couple minutes ago. This is your official formula. We're going to do that instead. Okay, so what's your partial derivative here? What's your partial derivatives of this guy? So in terms of x, the 2 comes down, makes a 14, right? So we got a 14x, the y goes away, times that delta x. I'll explain it here in a second. What's my derivative in terms of y? Does x's go away to y, times again, that's going to be my delta y right there. This is again my dz equals the stuff. So what's my delta x and delta y? It's the difference, it's a change from here to there. That's my delta, that's a change there. Notice that we're going from 1 to 0.95. So yeah, we're changing by the 0.05 difference, right? A distance, but it's now negative because we're going backwards, okay? Same thing with that, it'd be a negative. So I got a negative 0.05. Here I got a negative 0.1. And then we just kind of mush them all together. So the last thing is we need a numeric. This is our formula for it, but we need a numeric for what is x and what is y. Remember what it is. This is your x and y, isn't it? 1 and 1. So I got 14 times 1 times negative 0.05. Almost there. 2 times the 1, so negative 0.1. Calculator for sure, negative 0.9, and you're done. So that's the dz. That's your calculus stuff, because we did derivatives along the way. Your delta z is very easy. It's actually, here's a funny little formula, z sub 2 minus z sub 1. You're just taking a difference between them. But your z formula is this guy right here. So what I'm going to do is plug in each of those points individually. So first off, I'm going to say my second one was where I was going to. This is terminal minus initial. We saw that again back in vector land. These are all connecting ideas and thoughts. So I got 7.95 squared plus, was it a 2 or just y squared? Yeah, just y squared. What am I doing? That's not a negative. Sorry. Going back. See? It's not a negative, it's a positive. Sorry about that. It's just getting so caught up in all the connections. It was just so cool. So this is Z2 minus Z1 was my original. which is, again, just 1, 1, basically, like that. You just put all this in a calculator, and you get negative 0.8725. There you go. And again, that's my delta Z. Okay, one last problem. It's more words than anything, but the words are important, so let's talk about it. They give me a rectangle that has a length, I'll use just L if that's okay, length of 37 centimeters, and I have a width of 20 centimeters, and they're saying that there's an error on both the length and the width by 0.1 centimeters each. 0.1 centimeter error. So on the size of it, it could be plus or minus 0.1 centimeters. And then says find the maximum error for area. The max error for the area. Okay. So this is actually very simple. Area, capital A, is equal to length times width. So then my dA, let's do some implicit here. If you do implicit here, you would get WDL plus LDW. We have all of this stuff. The D, L, and DW, again, that's kind of like saying delta L and delta W. It's the same kind of stuff. It's this dA is kind of like saying delta A. I mean, again, what are they looking for? Either way, it doesn't really matter. It's practically the same in understanding. So then we got 37. My change would be that 0.1. And then I got that 20. Again, that change would be a 0.1. Now, this could be a plus and a minus, but to maximize it, I'm going to have them both positive so that they both increase the more to see what that maximum is. Again, you're wanting the biggest number possible. That the only way to make that happen is both of them be positive. Calculator, and I got 5.7 centimeters squared. That's a delta area. That's an error for my area. Okay, that's it. Thank you very much. Have a great day.